There are a vast number of ways to make an apple pie these days. You can simply purchase one from the grocery store, the nearest, sketchiest pie dealer, or tell grandma to get to work. The same can be said about the elements of the known universe. The elements can be created through primordial nucleosynthesis, known as Big Bang nucleosynthesis for you simpletons, or even through stellar nucleosynthesis. Now, join me on the search for the recipe for the creation of elements. The very first nuclei were formed through the primordial nucleosynthesis stage, otherwise known as Big Bang nucleosynthesis. This stage was incredibly short, lasting only about 10 seconds to 20 minutes after the Big Bang, the time period in which the universe was cooling drastically. It was in these conditions that the soup of protons and neutrons, floating pointlessly around, came together to form different atomic nuclei. The combination of protons and neutrons is not an easy one. Protons and neutrons violently collide, forming deuterium nuclei, which are the only stable isotopes of hydrogen. Along with the formation of these nuclei, photons are released as a byproduct. The two newly formed nuclei, having nothing better to do of course, merge together to form the nucleus of the next periodic element, helium-3, with one free neutron left over. Seemingly insignificant, primordial nucleosynthesis is actually the most vital part of the creation of the known universe, because it is responsible for the creation of the first four elements of the periodic table: hydrogen, helium, lithium, and beryllium.
Stellar nucleosynthesis is the process in which the nuclei is synthesized due to nuclear reactions, not the Chernobyl type, but the reactions that take place in the stars of the universe. The nuclear reactions that take place in a star are caused by the burning of elements in a star. This is the fuel that the stars use to guide it throughout its lifetime. The first stage in stellar nucleosynthesis is the burning of hydrogen, which gets converted to helium. All of the hydrogen in a star burns into helium in approximately 10 million years. Imagine waiting that long. Of course, our lifespan is only 76 years, while a star's is millions. During this process, energy needs to overcome the Coulomb-Repulsion forces among the protons. The Coulomb-Repulsion forces can either cause a particle to repel or attract a similar force. The second stage involves the carbon-nitrogen-oxygen cycle, in which these three elements are used as catalysts in order to fuse 4 protons and produce a whopping alpha particle, 2 neutrinos, and 2 protons. After all these reactions, helium nucleus is formed. Helium burning occurs right after the hydrogen burning is done, and a triple alpha process occurs. In the alpha process, the alpha particles, or the helium-4 particles, fuse together to form a carbon nucleus. All the helium burns into carbon in approximately 1 million years. Right after this occurs, and carbon is present, the alpha process begins causing the formation of neon, oxygen, and silicon. All of the carbon in the star burns into 100,000 years. The process that involves the decomposition of elements just keeps getting exponentially faster. The last element on the list after the star has decomposed the rest of the elements is iron. Iron cannot burn to form anything because iron is the most tightly bonded nucleus in nature. Once iron is formed, the star collapses under its own gravity, causing the start of yet another process. This process is responsible for producing the heavier isotopes. This collapse and forming of the final elements occur during the supernova nucleosynthesis. This whole collapse occurs about a fraction of a second, spewing all the elements out throughout the universe. These same elements are found in our left and right hand. Even the carbon, nitrogen, and helium that were once created by the star, these are all found on our planet Earth.